All right, well, welcome back. So my name is Aaron Standard. I'm one of the creators of Akka.net, and we're going to move on to Unit 1 of Akka.net Bootcamp. So if you catched our previous videos on Akka.net Bootcamp Unit 0, you've probably learned a little bit about the basics of working with actors, so basic actor syntax. We also introduced some side effects like working with different threads and all that sort of stuff. In Unit 1, which we're going to begin now, this is all about trying to actually professionalize your Akka.net applications. Now, with this unit, we're going to focus primarily on local application development. In some of the units we plan on releasing later, we're going to start introducing the network, persistence, and all these other fun little facets. But Unit 1 is where we're going to learn to cut our teeth on actually doing real domain modeling, real message design, and real testing of Akka.net applications. So without any further ado, let's go ahead and dive into the first unit. Okay, so to get back to Bootcamp, you can just go anywhere on the Akka.net website, go to Training, click Bootcamp. We'll scroll down here. I'm not going to sign up via email, and we're going to scroll to Unit 1, Building Local Akka.net Applications. So let's click the first lesson here. Now, the first thing that we're going to do as part of Unit 1 is we're going to learn how to use the Akka.Templates set of .NET New templates down here. So I won't bother reading all the descriptions to you, but I will go ahead and pull up our hyperlink to the Akka.net Templates project. So this uses the .NET New template syntax, which lots of other projects like ASP.NET Core, Blazor, Benchmark.NET, and others, they all use these as a way to A, distribute some command line templates you can use to scaffold new projects, but B, these will also install these templates so they're accessible through any standard IDE in .NET. So Visual Studio, VS Code, Writer, they will all work with these templates. So the first thing we're going to do is we're going to go ahead and install these using this little bit of command line syntax right here. Now, if you've already installed a previous version of these templates, this will go ahead and install the latest version, so that's all fine and good. And while we're here, we can kind of take a quick look at what we have available in the templates project. Now, this may be subject to change in the future, but this is what we're rolling with for now. We have the Akka.Cluster.Web API template. This one is pretty beefy. It's a big solution that has Akka.Discovery and Akka.Cluster and cluster sharding built into it. There's a lot of stuff going on there. We probably need to simplify that one a bit more. But the Akka.Console template, which is what we're going to use today, is a fairly simple template that uses Akka hosting, which is the infrastructure we're going to use for managing real Akka.net applications. So we're going to set that up. It also has a C# and an F# version. And then the other template that we're not going to use today is the Akka Streams template, which is basically just a little version of the Akka console template that uses some Akka Streams graphs. Akka Streams is great. We might do a bootcamp unit on it a little bit later this year. We'll have to see kind of what the demand for that looks like. But for the time being, let's just go ahead and install the Akka.Templates project. Let me fire up a console application here. Okay, that's all installed. Great. And then we can go ahead and see that we've got all these different little templates that you saw in the README all installed here. Okay, so we've just installed our templates. And now the next thing we're going to do is we are going to actually need to create a new solution. And then we're going to add our new template as a project to that solution. Generally, when you develop a .NET New template, you want it to be as unopinionated as possible. So in this case, it means shipping this as a standalone project template. Now, IDEs like VS Code and Writer have no trouble working with just a standalone, C# project, but Visual Studio really wants you to have a solution, so we're going to give it one. So we're going to create a brand new directory. Let me go here, go to Bootcamp. We'll make a directory. Actually, let's see if one already exists. Okay, we'll go to Akka Word Counter 2. That's the directory I created for this application here. And then let's go ahead and copy this. And this will help us bootstrap our project. We're going to create a brand new solution. We're going to add an Akka.Console application named Akka Word Counter 2.app to it. Then we're going to add the project to the solution, and then we're going to build it all. That should validate that everything works right out of the gate. So let's give that a little try. All right, looks like everything succeeded in about 6 seconds. Great. So we've got a brand new solution with a brand new project added to it. That's all well and good. Now, if we take a look at the directory where we went ahead and produced all this stuff, let me go ahead and clear my screen real quick. All we see in the directory right here is our solution and our app folder. Let's go ahead and take a look at what's inside the app folder here. We can see we have a C# project, a hello actor, program.cs, a readme, a timer actor, and then some global usings here. Okay, so this kind of matches what we see inside Bootcamp here. I'm going to go ahead and cut real quickly, and we're going to shift over to actually running our application inside JetBrains Rider, just so we can see what the template actually produced for us. Okay, so we've got the output from our brand new template sitting here inside Rider. Let's look at program.cs real quick. So program.cs, this is just a console application. So there's no ASP.NET Core, no HTTP routes, no network, no nothing. All we're going to see here is that we spin up a new host builder. If you were doing ASP.NET Core, this would be like your minimal web API builder or whatever. And what we see here is on the host builder, this configure services method. This is where we're going to start working with Akka Hosting. What configure services allows us to do is tie into this services right here is the iService collection. Whenever you're doing dependency injection in ASP.NET or any other like sort of Microsoft-centric web framework in .NET, you always use an iService collection to register your dependencies, which will be injected downstream later. Well, with Akka Hosting, which is one of the packages we're using here, in fact, if I take a look at our output, we're using Akka Hosting and Microsoft.Extensions.Hosting and .NET 9. All of this may be subject to change in the future. Don't worry about it. This is just basically what we're shipping with today. You can go ahead and upgrade any of this pretty easily. But the basic gist behind this is that we are calling this add Akka method right here. This comes from Akka Hosting. This is going to create an actor system with this name, and then it's going to run all these little builder functions that have been registered here. This works very similarly to how the dependency injection system works for the rest of the .NET ecosystem. But down here we have these little with actors methods. This is going to cause us to basically create an actor. In this case, we're going to create a hello actor. And then we're going to register this actor to the actor registry. That's the second parameter right here. We're not going to worry about the actor registry just yet, but what you should know is that this is a tool that allows us to basically register an actor using a type, and then we can inject that actor into other actors or other non-actor things, such as MVC controllers, background services, signaler hubs, gRPC services, whatever. Anything that supports dependency injection, we can inject it using actors this way. So the register method here is how we register a specific IActorRef, that's what this is, to a specific type in the actor registry for injection later. So we create a little hello actor, which just logs stuff out to the console. All right, great. And then we also create a second actor down here, this timer actor. This timer actor uses IWithTimers, a mechanism we're going to learn about in this unit, to periodically send itself a hello message, and every time we receive one, we're going to send it to this hello actor. All right, let's go ahead and see what this application does when we run it. And we can just go ahead and see at a rate of about once per second. We're going to go ahead and log these hello messages out to the console. Nothing all that revolutionary. So that's basically it for just this first part of getting the Akka templates installed. Now, I guess one last thing I should show is if I want to go and add a new project to, this is using JetBrains Rider, I should see this thing that I think is loading templates right now. Let me go ahead and pause it and give it a second to finish. All right, there we go. It took Rider a little bit to try to resolve some of this, but basically I can see down here all the custom templates I've installed in my machine. That includes installing another Akka console template, which can support C# or F#. And then I can also support Akka streams. And I've even got some other templates like a SQL Server database project template in here. So just kind of wanted to round that little capability off. Now that we've had a chance to go ahead and install Akka templates into our machine and use it, we're going to transition to the next lesson, which is all about actor hierarchies and domain modeling. Okay, so for our second lesson here, we played around a little bit with creating some actors in Unit-0, but we never really created an actor hierarchy. We just had a couple of top-level actors talking to each other. What we're going to want to try to accomplish with this next unit is we're going to try to model a richer domain. I probably skipped over this because I think we kind of outlined the goals inside the Akka templates lesson. But what we're going to try to achieve with Akka Word Counter 2 is a much more robust implementation of the application we produced in Unit-0. This time around, though, instead of trying to use, let's say, counting words out of some static text that we're just passing in via hard-coded constants in C#, we're actually going to try to pass in a set of URLs that we're going to download. We're going to then use an XPath parser to extract all the text features from it, and then we're going to do some tokenization and then count token frequencies that occur inside each of those pages. So this application is going to be doing a lot more than the old one did. But the basic thing that we want to kind of take a look at here is the notion of what the actor hierarchy is. Now, this application that we've just started doesn't have petabridge.command installed into it. Petabridge.command is a command line tool that's free. It's available for use as a .NET Global tool that allows you to manage Akka.NET clusters, but also local Akka.NET applications as well. One of the built-in commands that we reference here is the actor hierarchy command, which allows you to basically do a printout of the actor hierarchy in the local actor system you're running inside of. You can also, in theory, use a remote actor selection to print out an actor hierarchy for another remote process that's running somewhere else. And you can see some examples of us doing this here. Well, if we take a look at the output of the actor hierarchy command for like our draw together.NET code sample, this is the code sample that we use for teaching people how to integrate Akka.NET with Blazor. It's basically a multiplayer Microsoft Paint application. Well, the output of what that actor hierarchy looks like is going to be something like this, where we have a whole bunch of system actors. Some of these system actors have children. Then we have some user actors, and some of these user actors have children. This is sort of what an actor hierarchy looks like in Akka.NET. And this is a really important building block for modeling Akka.NET applications. Now, the key detail we want to pay attention to here is that we have two different root actors, the system root actor and the user root actor. The system root actor hangs on to all of the built-in actors that Akka.NET needs in order to run its own work. So as you can see here, these actors include things like the remote watcher and the remote terminator. These are actors that are responsible for making sure that Akka.remote connections get garbage collected appropriately. We have the system actors that run Akka.cluster, and we also have actors that run Akka.persistence, and we also have actors that run the logging system. These are all examples of built-in system actors that run internally inside Akka.NET. These actors are there to support your work as an Akka.NET end user. So one of the reasons why we have two different two different root actors is that the system actor always shuts down only after all of your actors shut down in the event that we need to terminate an actor system. So that's the really big reason why we keep these two separate. The other reason is that the system actors might be configured to run on a separate dispatcher that has access to its own threads or whatever. Right now, everything uses the .NET thread pool because that's the configuration that tends to work best for the most applications. But this gives us the option to kind of separate those if we wanted to. The user root actor, this is where all of your stuff's going to go over the course of the lessons that we're working on here in Bootcamp and anytime you're working with Akka.NET in the future. So just to kind of give you a rough visual of what the actor hierarchy looks like, both the system and the user actor report back to a parent, which is called the bubble walker. Basically, this is sort of the root actor of everything. The way that your actors will end up getting modeled is all of your actors are going to be top-level children, at least, of the user actor. This means that they are directly descended from the user root actor. And then if those actors themselves spawn children, they will go ahead and be allocated a little bit further down the actor hierarchy. This basically kind of works a little bit like a folder or a file architecture. The path for one of these child actors is going to be composed of all the parts that make up its parents. So you have the full absolute path of this actor will be /user /top-level1 /child. And you can go ahead and see that in the petabridge.command output that we included in this lesson here. So the next question you might be wondering is, why have child actors at all? Wouldn't it make more sense just to have a totally flat actor hierarchy where everyone's equal? And the answer to that question is, it depends. Generally speaking, many applications benefit quite a bit from having an actor hierarchy for several reasons. The first big reason is that it actually makes modeling domains quite a bit easier. Domains tend to be composed of, let's say, large feature areas that represent one facet of the business. So you might have a feature area for accounting and another for payments and another for fulfillment, etc. Each of those big areas is comprised of lots of sub-entities and sub-activities. And now you can see where I'm going with this. It's very easy to decompose all those different, let's say, actors or all those different entities. You can use those terms interchangeably if you want to. It's very easy to decompose those hierarchically. A payment might belong to an invoice, and that invoice might belong to an account. And you can kind of go ahead and see a bit of a recursive model for defining all of this. So using hierarchical modeling is actually a very natural and intuitive way to express relationships that occur naturally in the business domains that we want to model with software in the first place. The other advantages to having an actor hierarchy is that A, it makes it easy to kind of reason about the life cycle of entities. So for instance, if I need to shut down an account entity, I want to make sure that all of the other entities that depend on that one being alive get shut down with it. Well, the way actor terminations work in Akka.net is if you terminate the parent, all of the children are going to get terminated too, and that's going to apply recursively all the way down the actor hierarchy. So if we want to shut down an entire actor system, we just issue a termination notice to the user actor, wait for all of them to shut down, and then we issue a termination notice to the system actor, and as soon as the system actor shuts down, we know that all of its children have already previously shut down. Therefore, it's safe for the process to exit. So having this sort of parent-child relationship makes it very easy to reason about life cycles. And then finally, probably the biggest bang for our buck is going to be fault tolerance. We use what's called a parental supervision model for dealing with unhandled exceptions in Akka.net. We have a whole video on how actors restart that I recommend you watch if you want to learn more about that. But the basic gist of this is that if an actor throws an unhandled exception, its direct parent is the actor responsible for deciding what to do about that exception when it happens. And generally speaking, by default, we're going to instruct actors to restart. That means we're going to reuse their props to recreate the actor exactly as it was when it was first started. This is kind of like the equivalent of taking a failing process on your Windows, Linux, or Mac and killing it and then restarting it from scratch. Have you tried turning it on and off again, as the saying goes? That's the approach that we're going to use as our sort of general fault tolerance strategy for handling unhandled exceptions. And it works very, very well across most contexts. So this is sort of the basis for why we even have child actors in the first place. Now we're going to go ahead and move into actually trying to model an actor hierarchy for our Akka Word Counter 2 application. All right, so Akka Word Counter 2. Well, we know based off of the requirements that I briefly mentioned earlier that we need to parse and extract text from multiple web pages. We need to compute a running total of word frequencies per page, and then we need to manage total job execution. We want to take the results of all pages and then merge them together at the very end. So this division of labor is something that we can model fairly easily with actors. Off the top of my head, my initial default approach for modeling this would incorporate these four actors. The ParserActor will do all of the heavy lifting of downloading all the web pages and then running the output through an XPath parser, like I think in this case we're using HTML Agility Pack. We'll go ahead and use that to extract all of the raw text, and then we can pass that along to the Word Counter Manager. This Word Counter Manager is going to use a very popular actor hierarchy design pattern called the child per entity pattern, where for each unique document that we parse, we're going to create a document word counter actor who owns 100% of the state for just that document. So if you have 100 documents, you have 100 children. If you have one document, you have one child. This gives us a very scalable and repeatable approach that keeps our state management really simple for working on any individual document. We have the document word counter itself. It's basically going to be responsible for doing the counting and the state management. It's also going to keep track of who needs to know about the completed counts once we have them. And then finally, we have the WordCountJobActor. This is the actor responsible for owning the entire job. That includes both the parsing, the configuration, and the actual final result. You can kind of think of this actor like a little Saga or a process manager. And the way we might represent that as an actor hierarchy is going to basically be, we have our user's root actor here. We're not going to be defining any system actors because this is all application code. So we're going to have our parsers little actor hierarchy here. Now you'll notice this has a bunch of what appear to be like randomly named children. We're going to create a special type of actor called a router. And that means that instead of creating just one instance of our parsing actor, we're going to create and we're hinting at it here in the written documentation. We're hinting at basically using what's called a pool router, which means we get n, where n is some value greater than 0, identical actors that are all going to get work routed to them using some sort of work distribution algorithm. So we're going to see a little bit more about that later in Unit 1. That's going to be the first portion of our actor hierarchy. Then the second portions are going to be the word counts actor. This is where that child per entity approach comes in. And then finally, we're going to have our Saga actor, this word count job actor. It's going to be the one kind of directing the flow of traffic for everybody else. So that's our actor hierarchy. Now, the right place to begin designing an Akka.NET based application isn't to jump straight into defining actors, because that's actually kind of putting the cart before the horse to some extent. No, the first thing we need to do is actually define messages. Akka.NET is an event-driven system. Without events, there isn't a lot of interesting stuff that we can do. So we need to sit down and define those first. All right, so the next thing we're going to do is define our messages. Now, one of the things that I'm going to do real quick as a segue is we're going to define a value object. This is basically a way of trying to avoid primitive obsession and help make our application not be able to represent a legal state. And in this case, one of the requirements we have is that any document that we're going to download and parse, that has to be defined as an absolute URI. That's one of the things we need to implement. By the way, I've got a great video here on using this type of pattern called Make Illegal States Unrepresentable. This is more about mathematic errors, but I'll go ahead and include a link to that in the description. For now, the first thing we're going to do is we're going to create a brand new file. So let me pull this up, get rid of that. We're going to create a brand new file called messages.cs. We'll just call this messages. I'll get rid of that. Don't need it. And then I am going to type this code in here. Now, I copied and pasted the command line earlier. I really think typing all this out is a good idea. This will actually help you really kinesthetically kind of learn some of this stuff. So that's something that we're going to do here. So I'm going to go ahead and create a public record struct. We want it to be immutable called absolute URI. And we'll go ahead and, did I pass in a string or did I do a URI? No, I did a URI earlier. Okay, let's go ahead and do that. We'll go ahead and do a public constructor. That all comes in. And then I think I need to go ahead and I wanted to go ahead and override the toString function to just go ahead and do return. In fact, let's do this. I'll make it look a little nicer. We'll go ahead and do URI.toString. Then I want to throw an exception here. There we go. That's perfect. We'll do that. I don't think I necessarily need to make this init. In fact, I could probably make this a read-only record struct if I wanted to. I think that looks okay. Yeah, that looks pretty good. Let's see. I guess they called it value. All right. Well, when I say they, I mean me. I'll go ahead and rename that. Yeah, let me do that real quick. Call that value. Yep, that's fine. Okay, all done. So we've got our absolute URI. This is going to be the key type that we use for identifying our documents throughout all the messages that we're about to define. So that's why we're doing this part first. And, you don't have to mess around with structs necessarily or any of that jazz if you don't want to. But I think this is fine. We're just going to roll with it. Now, the next thing that the tutorial is going to have us do is this is a really common pattern that we use a lot in Akka.NET applications, which is using a marker interface. This marker interface has a little bit of heft to it, though. It's not just a pure marker interface where it has no members. We're actually going to define a member here, the document ID. So I'm going to go and implement this real quick. IWithDocumentID. Let's do that. Public interface. IWithDocumentID. And this is an absolute URI. So let me go ahead and change that. Perfect. And if you want, you can leave a comment. I think it's pretty self-explanatory, so I'm not going to bother. But the basic gist is that you can program messages in Akka.NET to handle an interface rather than handling a concrete implementation of it. So if I go and expand the number of let's say, messages that implement the IWithDocumentID interface in the future, actors like the word counter manager that spawn child actors that do all the concrete handling, that actor you don't necessarily want to have to update to basically say, oh, well, now these two new message types you have to route. Given that it does the same thing with these messages regardless of their implementation. It routes it to a child. That's what it's going to end up doing. So having an interface that actor can be programmed against instead of a concrete type makes it much more future-proof in the long haul. So that's what we're going to do here. We're going to create this IWithDocumentID interface. Now, the next thing we're going to do is we're going to go ahead and begin defining a real message taxonomy. Now, I believe we covered some of this in Unit-0, but we're going to expand it in a little bit more detail here. A true message taxonomy in Akka.NET usually consists of three message types: a set of commands, a set of events, and a set of queries. Commands are requests to do something, and a command might need to get validated. So for instance, we might need to double check that this scan document command has, a document ID that the system, is aware of or whatever. We kind of took most of the validation out of the equation here by basically forcing this URI to get validated as an absolute one. So that's kind of the only real big thing we can do other than trying to download the document to validate it. So the commands might be subject to validation. Events are not subject to validation. These are basically units of record, where every time an event occurs, it's basically an instance of something actually happening in the real world. The document scan failed. Words were found. We reached the end of the document. We finished tabulating counts for the document, etc. So events are things that happen. They don't get validated, but we may not necessarily use every event that ever gets produced. If a document scan failed event comes in, we probably aren't going to update the state of, let's say, one of the actors inside our system, but we might pass that along to the original caller, for instance. That might be something we do. Or maybe we will incorporate it. It's kind of up to you what you want to do with it. And then finally, we have queries. Queries are basically things that don't, commands impact state, events are state. Queries kind of exist independently from state. They're really there as a means to describe which state changes or which pieces of state does this caller need access to. That's really what a query is all about. There is technically a fourth type of message, which could be considered to be like a response message, where it's a response to a query or a response to a command. We're going to go ahead and implement all of these commands and events. So let's go ahead and do that together. Now, again, I strongly recommend that you type all of these out. I already typed all these out. I wrote these lessons, so I basically have the muscle memory here. But if you haven't developed it, you probably should. So let's go ahead and incorporate these directly into our code. Okay, so I copied and pasted the events from our lessons on Bootcamp directly into my code. I'm getting some complaints here. I think I need to import the immutable namespace. Okay, let's go ahead and reiterate real quickly a couple of things we're doing here. One is that I'm actually creating a static class, document commands, and then all of these individual messages are basically subclasses of that type. Now, the reason why I'm doing that is just because this is a style thing. There is zero technical benefit or advantage to doing it. When we actually start implementing the actors, you'll see me use like a using static to go ahead and import this namespace. That way I only need to refer to the scan document or scan documents messages. But from an organizational standpoint, this kind of helps me keep my stuff organized. That's why I like doing it. You'll also notice that my scan document implements IWithDocumentID, but scan documents does not. So if I have to pluralize a command, I may not apply a marker interface to it. Again, we're doing things because they make sense. We're not trying to be religious about it. So there's only one actor that can handle a bulk set of documents, and it does not have any parents. It does not have any routing sitting in front of it. It's the Saga actor is the only one who knows or cares about this. Therefore, we're not going to bother decorating that message with a new type. There's no point in doing that. The other thing that I might sometimes do in my more fully featured applications is do something like this: public interface I document command I with document ID. And that's a real marker interface, and I might go ahead, did I spell document right? Yes, I did. I might go ahead and apply that here to basically make it possible to distinguish commands from events from queries by inspecting their interface type. I'm not really bothering with that in this application because our domain is so small. It doesn't make a large amount of sense to go ahead and do that. So again, one of the things you'll hear me iterate constantly through all of our tutorials is be practical, not religious. That's what we're doing here. So we have all of our events incorporated. Now, one other thing that I believe I mentioned in Unit-0, but maybe it bears repeating here, we want to make sure all these message types are immutable. So that's why you'll see us use records everywhere. We'll use immutable dictionaries or read-only lists. We can kind of interchange those. If this read-only list is truly implemented under the covers by something like an array or a regular list type, and a user wants to cast it and do some work there, you're not going to be able to prevent really determined idiots from doing bad things inside your software. I mean, try as you might, you're going to end up basically being defeated eventually if they're determined enough. But what we want to do is prevent simple mistakes from happening. And that's what these interfaces help us do. So with the immutable dictionary, it's not possible for us to accidentally mutate and introduce side effects if multiple actors all receive the same message. So that's why we're doing it there. With a read-only list, it prevents people from accidentally creating a side effect by overwriting an item. That's the reason why we're doing all this. And then, okay, so we got our document queries set, document events, document commands. I think that is it for everything that we have done so far for this unit. So we kind of talked about the hierarchy we're going to model. We created all the messages we're going to use to communicate with it. In the next unit, we're going to go ahead and actually begin designing the first of our actors, the document word counter. And we're going to learn about a couple of really important features of Akka.net, namely behavior switching and receive timeouts. So let's dive into that next. Okay, so for this unit here, behavior switching and receive timeouts, we're going to start working on implementing our first real actors inside Akka Word Counter 2. The first concept I want to introduce here before we start writing code is the notion of a finite state machine. Now, if you got a computer science degree, you probably got introduced to this, I don't know, sometime around your CS 200 2000, or 201 course when you were learning algorithms and data structures. A finite state machine is a really useful way of being able to express, let's say, a multi-stage algorithm or a multi-stage entity in the case of something like Akka.net. Where in this instance, we might have, let's say, in our word counter actor, we have our initial on receive stage where we are waiting to receive some instruction to begin processing. There's not a lot we can do. Like, we can't really respond to queries yet while we're in this stage. We don't have anything to report back on yet. Once we begin running, now we're in a running stage, which means that we cannot accept another request to begin a job right now. That's an example of, let's say, a behavioral difference occurring between state transitions. And then finally, in the completed stage, we can go ahead and report on our final output, but we can't accept any additional input to change that output, nor can we accept any additional jobs. The idea is that during a finite state machine, there are discrete transitions from one state, on receive being one state, running being another. There's a discrete combination of events that will result in us transitioning from one stage to another. When we change stages inside a finite state machine, stages or states, those terms are interchangeable. When we transition from one state to another, the types of things we are allowed to do and also what our state might represent can change as part of that. Now, actor behavior switching is the really powerful tool we have inside Akka.net that allows us to express all of this internally inside the implementation details of a single actor, which is where you want it, by the way. If you're a caller sending a message to an actor, you do not want to know or care what state that actor's in and what it can do. All you want to know is, hey, if I give you the information, do the thing with it. That's what behavior switching is going to allow us to do here. All right, so we're going to talk about modeling the document word counter actor. Now, there's a handful of definitive events that we've already defined. Once the end of document reached event is received by this actor, we're done counting. So any more word founds that we get, we don't care. We're done. If we get a fetch counts message before we're done tabulating the results, we could decide to send over a partial result right now, but that'd be really stupid. The better thing to do is don't make the caller think. The caller should not have to poll for getting the completed results back, which is what it really wants. Just buffer that request and who sent it until we're done. Then we can go and answer each of these queries. This is one really pivotal difference between actors and something like ASP.NET Core. In ASP.NET Core, you got no choice. You have to respond right now. With Akka.net, we can wait a little bit and simply defer processing of messages until we know we've received all the events we're looking for. Then we can go and reply back. And that's what this state machine kind of shows. We have our on receive event here. We are going to wait until we start getting these words found messages that come in that'll cause us to transition to this sort of active state here, where we're just going to keep processing those words found until we get this end of document reached event right here. Once that happens, we're going to transition into this sort of done state. And anytime we get another IWithDocumentID, we're going to log a warning. And then eventually we're going to use a ReceiveTimeout to passivate this actor and shut it down. ReceiveTimeout is another thing we're going to learn about in just a second. But that's basically the equivalent of, if you're familiar with finite state machines already, ReceiveTimeout is one way you could implement a state timeout, which is a very common facet of FSM. Let's go down here. Now this looks like a fair amount of code to go ahead and implement. This is our document word counter actor. Again, you should type this out. Let's go ahead and start this up. And I'll go down here. We're going to go ahead and create our document word counter actor. All that. Now, the actor type that we're going to use here, I believe, is an untyped actor. Let me double check that. Yeah, we're going to go ahead and create a little untyped actor. All right, I'm going to go through the trouble of implementing all this, and then we will confer once I'm done. Okay, so I have finished implementing the DocumentWordCounterActor. Now, one thing I didn't do, and I think this is probably mentioned in the written tutorial, but I'm trying really hard not to just read it line by line in order to make the video a little more compelling. This really does belong in like an actors directory, so I'm going to move it in there. Okay, there we go. So what are we doing here? Well, the first thing we're doing is that this actor belongs to a single document ID. For every unique document we are going to process, one of these actors will be created. We're also going to get a hold of the Akka.net logging system. You've already seen this several times. And then here's our real state. We're going to have a dictionary that refers to a term and the number of times that term appeared. These are our word counts. This is a mutable dictionary. We can make this immutable if we wanted to, but honestly, it just was easier for me to do it this way. And then we have our hash set of all of our subscribers. These are all of the different requesters who wanted access to our state before it was ready necessarily. So what's going to happen down here is we have our receive method, and we're going to look for when we get a words found message, when the document ID equals our ID, we're going to go ahead and log all these words were found inside the document. Then we're going to basically take all these tokens, and we're going to use this to increment our token counts. All good. When we get a fetch counts message inside the state, we're just going to take the sender and add it to our set of subscribers so we can get them a notification later. When we get an end of document reached message, we are going to prepare our final counts tabulated for document. And most importantly, we're going to convert that mutable dictionary into an immutable one using a little bit of link. That way, if we end up sharing that dictionary across multiple consumers and one of them modifies an element on it, it doesn't produce any side effects that way. All right, sounds good. We're going to loop through a list of subscribers, send each one of them a copy of that message, and then we're going to clear the subscriber list. And then this is where we transition to our complete state. We call become complete. That's going to cause us to go from using this method to process messages to using this one. So that's the state transition right there. Finally, we are going to basically say if we get a IWithDocument ID that corresponds to a different document than what we're processing, we'll just log a warning and ignore the message. Otherwise, we have this little receive timeout down here. We're going to talk about that in just a second. But if we get this receive timeout, we're done. We're kind of ending somewhat prematurely. We're just going to go ahead and shut ourselves down. Means that the job didn't finish for some reason. And then finally, we have our default behavior, which is just logging the message as unhandled. This actor uses a lifecycle method called pre-start. Now, this is something that you will see us use throughout many of our samples. This is a method that gets invoked before the actor ever processes its first message. And what we're going to do here is schedule a receive timeout to arrive 2 minutes into the future. Receive timeouts are essentially a sliding window timeout. It means that timeout gets reset every single time an actor receives a message. So whenever an actor receives a message, that's going to reset the receive timeout back to its original 2-minute threshold. If we go more than 2 minutes without receiving a message, we will receive this receive timeout message right here, which will cause us to shut ourselves down. Now, if we want to design it such that a message does not get counted against the receive timeout, we can actually decorate a message. I'll go here for just a second. We can decorate a message with the I.not.influence receive timeout, and that'll cause it not to factor into the receive timeout calculation. But for all intents and purposes, we are perfectly happy with our messages defined the way they are. Now, when we shift gears to our complete state down here, we are going to, if we get another fetch counts message, we're going to go ahead and tell the sender all of the completed tabulations right now. We're just going to go ahead and do that. Otherwise, if we get any other message here, we're just going to log a warning. And then eventually when we get the receive timeout, we're going to shut down. So one really important design trait that I think a lot of C# users would completely miss and overlook is the fact that the caller, the one who wants to know about our word counts, doesn't need to know or guess where we are with our processing. We're going to do them the favor of waiting until we know we're done before we send them the reply back. This is going to greatly simplify the amount of code the caller has to have in order to do its job correctly. There's no polling inside this system, in other words. Everything's all done on an event-driven, deterministic basis, which is good, understandable, safe, and easily repeatable. That's the goal. We want to go ahead and make it the receiver's responsibility to figure out how to do the right thing to make it easy for the caller. So with that being done, I think we've talked a bit about switchable behaviors and receive timeouts. You can go ahead and review the lesson if you want to get a little bit more details. But the next thing we're going to learn how to do is we're going to dive into the Akka.NET Test Kit to author some unit tests for working with the document word counter. All right, so on to the next lesson here. We're going to go ahead and learn how to use the Akka.NET Test Kit. Now, the basic gist here is this whole section of the lesson is basically a big sales pitch for the Akka.NET Test Kit. Here is in broad strokes, why it's a great idea to use the Akka.NET Test Kit. The first is that we manage the lifecycle of the actor system for you, and we guarantee you that every single actor system basically every single test gets its own unique actor system. This is designed to prevent cross-pollination and all sorts of other weird stuff from happening. Finally, actors are asynchronous. The test kit makes it very easy to test the asynchronous behavior by providing you with a lot of first-class testing utilities that make it really easy to assert the actor did the right thing. So, trying to write unit tests for actor-based stuff without the test kit, you can certainly do it. You will have a much easier time if you just trust us and use the test kit. So that's what we're going to do here. The first thing we're going to do is we are going to add a new project to our solutions. Let's go here. I'm going to add new project. Let's go to, we'll go ahead and do unit test. We'll do .NET 9, and we'll go ahead and call this Akka word counter 2.app.tests. And we'll use XUnit. That's what we're going to use today. All right, that sounds good. We'll go ahead and do that. So let's let that get baked in there. All right, so now we're back here. So we've gone and we've created our test project. And one of the things that we can do is we can go ahead and take the XML from the most recent version of the project here, and we're just going to go ahead and paste this in. I think it's a great idea to type actors. I don't think it's a great idea to type in MS Build. So I'm going to go ahead and just copy this, go over here, and then let me go ahead and edit this project here. There we go. Let's go ahead and compile everything real quick. All right, that all works. So what did we just do? We installed two different packages, the Akka.TestKit to XUnit 2. That's what we're going to use right now. There's also a bunch of XUnit dependencies we passed in as well. We also referenced our application here, so that's all working. And then the other thing we did is we installed the Akka.Hosting.TestKit. We're not going to use that a huge amount right this second, but we are going to feature it pretty heavily when we start doing integration tests a little bit later in this unit. So this gives us kind of a good foundation to start from here. Now, the next thing we're going to do, if I go back to Bootcamp, is we're going to author our first test kit test. So I'm going to do this. First thing I'm going to do is, let's see, this is the document word counter specs. Let me go ahead and copy this right here. I'm going to go ahead and basically rename our little test class, do that. I'll delete this. Oops, I think I did the wrong thing. Let me go ahead and import the XUnit2.testkit. So the test kit is basically where all of our testing infrastructure is going to come from. That's what's going to configure an actor system for us. It's also going to spin up a whole bunch of useful testing actors that make it easy to author assertions. That is all good. We like good things. So we're going to go ahead and do that. Now, another thing I'm going to show you how to do is how to actually configure the actor system that we're testing. I'm going to copy this little bit of HOCON configuration right here. HOCON is basically typed JSON. That is still the underlying configuration system that Akka.NET uses. When we're using Akka.Hosting, Akka.Hosting is basically authoring our HOCON for us. HOCON is a fine standard, works pretty well. It's still what Akka.NET uses internally. We just try to hide it as much as possible from you. The Akka.Hosting.TestKit eliminates the need to work with HOCON at all, basically. But down here, we're not working with things like iService collections and any of that stuff. We're going to use HOCON to configure our application. So we'll generate a little bit of HOCON. And the next thing we're going to do is we're going to go ahead and define a constructor that takes an iTestOutputHelper. And then we're going to call the base class constructor. And I'm going to pass in our config. And then I'm going to pass in our output helper. Call that output. All right. This is an XUnit thing. What this is going to do is the Akka.XUnit.TestKit knows how to take the output helper. This is what writes standard output from your test directly into the XUnit test logs. This will make it easier to review things that went wrong or errors that happened inside systems like GitHub Actions or Azure DevOps or really any other CI/CD system. This is a good habit to get into. Use the test output helper. We're going to pass that to our base class along with this Hocon configuration, which is going to increase the log level from info, is what we use by default, but we're going to use debug in this case. All right, now let me go ahead and rename the file type to match name real quick. All right, that's looking good. Now, what does this test have us do? Next, we're going to go ahead and create a test document URI we can leverage. That sounds good. Let's go ahead and put that right here. That way we don't have to type that out each time. Perfect. Then we're going to go ahead and define our test method, which is should process word counts correctly. All right, doesn't get much simpler than that. Let's go ahead and type that out. Oops. Should process word counts directly. Let's use a fact attribute here. And then I personally use the arrange act assert pattern. You'll probably find a million articles online about how there's better ones. I don't really care. But that's basically what we're going to do. And what we're going to do here is we're going to go ahead and create our test instance of our document word counter actor. And we're going to do this the same way we would start this actor in Akka hosting or anywhere else. We're going to go ahead and basically just use the built-in, the sys property inside the test kit. This is the actor system that's managed for you inside each of these unit tests. So let's go ahead and paste that in real quick. All right, that's going to give us our test actor. All right, that's all looking good. And then we have some test data right here where we're going to pass in some messages. Let's go ahead and copy that. All right, these are all the different words that we found. So in order for this actor to basically give us all the counts back, we need to pass in these words found events. And then at the very end, we need to pass in this end of document reached message. All right. So once the actor receives this message, it's done counting. It should transition behaviors at that point. Next thing we're going to do is we're going to have the test actor subscribe to updates. So let's go ahead and do that. I guess we're doing that as part of the arrange step. All right. This guy is the test actor. And the test actor is actually the implicit sender for all messages that are authored inside a test kit test like this. So by implicit sender, I mean I could delete explicitly setting it as the sender and this test would still work. But the reason why I'm putting it in here is to make it obvious what's happening. The test actor is a special built-in actor whose mailbox is assertable inside a test environment. And you will see an example of that very soon. So we're going to do that. And then we're going to go ahead and deliver. So what we're doing here, by the way, is we're having the test actors subscribe to basically send a query saying, hey, I want you to get the total document counts back. That's what we're going to specify. And so the actors, we're going to be going to send that message first. That way we know that this, remember, actors process messages in the order in which they were sent. So this subscription gets sent first. And by the way, it actually wouldn't matter if this subscription was sent first or last. We would still get the exact same result because of how we defined the document word counter actor. So we're going to do that. We're then going to go ahead and loop through all these messages and tell them to the actor. And then at the very end, we're going to assert that this actor, let me go ahead and copy all this. We're going to assert, this is where the test actor's magic comes in. This expect message async basically is telling the test kit, we expect this message to be the next one to arrive, and it has to arrive within 3 seconds by default. That 3-second value is configurable via the Hocon we can pass into our test class. But 3 seconds is the default. We are expecting 6 distinct words to appear in this response. So let me go ahead and run this test, and we should see it pass. All right, great, that test passed. Let me go ahead and use some code coverage real quick. And we can see which parts of our actor got fully covered with tests. Okay. Let's take a look here. And actually, I'll just jump over to the word counter actor. What all got covered with tests? Looks like our ReceiveTimeout and our unhandled message stuff. So none of this stuff got covered with tests, but all the meaty stuff up here did. That's very good. And then nothing in our completion behavior got covered with tests. But you know what I can do to kind of pump up our test coverage just a little bit? Let me go back to this test and I'm going to write, let's go ahead and do this one more time. We'll go ahead and send this. And then, we'll go ahead and expect another response back. Let's go ahead and cover all these tests. And lo and behold, if I go back to my document word counter actor, now we can see that the complete behavior got hit here and that we're able to tabulate the document again and that its results pass. Now, 100% test coverage is never really the goal. That's kind of a bit farcical, if you will. but we have done enough to kind of prove that we have reasonably well covered the document word counter actor. Now, if we take a look down here, I talk a bit more about configuring the actor system and all the different flavors of TestKit that we have to offer. We support every major testing framework, so NUnit, XUnit, MSTest, etc. That's all pretty well supported. But the test actor is the real MVP here. We're going to do some more tests down the road, probably using the Akka.Hosting.TestKit, and there's a lot more functionality than just expect message async. If I dive into here real quick and go to our test, and I take a look around, I can expect basically that an actor died. I can expect a message from a specific actor. I can expect an array of messages. I can do things like fish for message, where I'm going to wait until a message that satisfies this predicate arrives. There's lots of different tools available for testing message handling. And there's also more tools for the test kit than just the test actor. So we'll get to see some of those as we keep going here. But for the time being, I think we've done it for this lesson. And the next section here, I think we're going to begin learning about working with and spawning child actors. So now we're on to our next unit, working with child actors. So far throughout Akka.net, we've only used one actor base type, and that would be the untyped actor. This is the simplest possible actor type, and it's basically just there because all you really need to do in order to process messages with it is just write a switch statement. Well, the next actor type we're going to look at is the receive actor, which is a higher level abstraction on top of the untyped actor that we created. And this was back before pattern matching with switch was implemented in C#. But there's still some niceties about working with it. In particular, I find it's very easy to work with receive handlers that need to define like awaits and async operations in it using the receive async syntax. I personally prefer using receive actors for that over the untyped actor. So we're going to go ahead and learn how to create a receive actor inside our application by creating the word counter manager. This is the parent actor of the document word counter actor that we just created. Okay, so we're going to go into the Akka word counter 2.app/actors folder, and we're going to create a brand new actor, the word counter manager. So I'm going to copy that real quick. We'll go into Writer, we'll go into here, add a new class, word counter manager. I'm going to make this class sealed, and then I'm going to have it inherit from receive actor. All right, all seems pretty well and good. And then I guess we only really have one receive that we need to define, which is this I with document ID right here. So let me go ahead and create a constructor real quick, word counter manager, and we'll define a type receive. We'll go ahead and do I with document ID, and then we will go ahead and create child actor name. And let's see, this all needs to be, I think, Uri-Encoded. Let's see, how do we do this here? Okay, that's the little piece of code that I needed right there. So I'm going to put a little comment here to explain what this does, which is that all actor names must be Uri-Encoded. And we'll go to import that. So that is actually an important requirement for working with actors is the names of, let's say, I guess I call this S. I'll rename it S, fine, whatever. The basic gist is that all actor names need to be URI encoded. So if we're getting something like a document ID, which is itself an absolute URI, we might need to go ahead and run something like the HTTP utility.url encode on that in order to make it work correctly. Okay, next we're going to go ahead and do child equals child.getterElse. This is a little extension method in Akka.net. And let's see, I think we just need to return, we just need to go ahead and return an actor here. All right. And what I'm going to do, that looks correct to me. Yes, it does. Great. So here's what this piece of functionality does. We are going to see if we have a child already named after this document. If we do, we'll just use that. If we don't have a child named after this document, we are going to create one. We're going to go ahead and pass in the document ID here. We are going to then also call context to actor of. This will create a child actor named after the document ID. The important thing we need to do to make sure that this works consistently is we need to make sure that the child actor is named after the document it represents. If we don't do that, this whole methodology falls apart. So that's really kind of an important facet here. So this is going to basically perform a create if not exists pattern, which is something you'll see constantly in Akka.net applications. It also gets used in places like SQL. It's kind of another area where that's popular. So we're going to create, and I'll just go ahead and make this an IActorRef. Let me go ahead and do that. Just so it's nice and clear what we're doing. And then we're going to forward the message. Basically, forwarding the message is a way we can make sure that when the actor receives this message, it looks like it came from whoever sent us the message, rather than it looking like it came from the word counter manager. So in other words, the fact that there is this kind of parent actor sitting between the original sender and the child, this is going to help the parent actor not show up as the sender. This makes it kind of easier to preserve the chain of communication inside Akka.net. Now, this is a really common strategy. It's just called forwarding. Another approach you can use if you want to make sure that the child actor always sends the reply back to the correct recipient at the end is just to include an IActorRef inside your message definition. That's the other approach you can use for doing this. But for really, most applications, forwarding is probably good enough. All right, so we've taken care of that. This kind of explains all the details. So I guess we're going to move on to the next lesson, which is all about actors and async await. All right, good stuff. Let's go ahead and learn a little bit more about that. Okay, so we're going to get into working with the ParserActor and doing a little bit of async await. So the ParserActor has a pretty straightforward job, albeit it basically involves a fair amount of I/O. The ParserActor gets a instruction to scan a document. So the first thing we do is we download that web page. In the event that the download is successful, we are going to use HTML Agility Pack to extract all the text in that page. And as we discover, groups of words on the page, we're going to go ahead and send those in batch to the sender. And then we're going to send an end of document reach message once we're at the end. That end of document reach is important for signaling that there's no more text to be expected from this page. The other actors that are participating in this application don't know about it. In the event that the download fails for whatever reason, we're going to go ahead and send a document scan failed. And also in the event that the XPath parse doesn't succeed either, maybe because, I don't know, the document's encoded weird or it's not an HTML document or whatever the case may be, we'll also send a document scaled event for that as well. So the first thing we're going to do is we're going to go ahead and install both of these packages into our application project. So I'm going to go ahead and pull up my little command line here. Let's move to the app, run both of these. That all looks good. Boy, I guess .NET 9 is a little bit more verbose on installing packages than I remember. But okay, yeah, good times. Okay, that all looks like that went through. Great. The next thing we're going to go ahead and do is we are going to create a little utility class. This is basically just going to do the HTML Agility Pack text extraction for us. I like keeping this sort of business logic separate from the actors that use them because this will help simplify testing if we needed to do that. So let's go to our project. And what's the name of this class? This is the text extractor. I'm going to go ahead and copy that. Yeah, go ahead and do this. Let's go to add class, text extractor. And I'm just going to go ahead and copy and paste this code. Go ahead and paste that in here. That all looks good. This took a little bit of finagling for me to figure out how to do, namely how to do some of the tokenization and how to filter on some of the scripts. So I saved you a bit of trouble there. We'll go ahead and leave that as is. Now, that is all well and good. That's all just sort of the setup and infrastructure so far. The really big thing we want to focus on next is the actual actor implementation. So with all the dependencies installed, we need to go ahead and actually build our ParserActor. And that's what we're going to do next. So I'm going to go ahead and just copy this ParserActor. And we are going to go into actors, ParserActor. And did I make this a ReceiveActor? No, I made it an untyped actor. Okay, well, whatever floats your boat. We'll go ahead and make this an untyped actor. And I usually seal all my public classes. This just is kind of a force of habit at this point, but also it does provide a minor performance benefit doing some of that stuff. Okay, I'm going to go ahead and seal all that. And then we have our dependencies. This actor relies on an HTTP client factory. That's why we installed that Microsoft.HTTP package. Microsoft.Extensions.HTTP. This gives us the HTTP client factory. This basically pools HTTP clients together and allows us to kind of reuse them across multiple requests. We're not doing nearly enough HTTP traffic to even need this, but this was just a good opportunity for us to kind of showcase how to use dependency injection in Akka.net. Okay, so that's all available. Now, let's take a look down here. The actual message handling we're doing here is very simple. There's only one type of message that we handle. The more interesting piece of the puzzle here is this handle document handler right here, which takes an absolute URI. Copy that signature real quick. All right. So we get a document that we need to handle. So the first thing we need to go ahead and do, if we take a look here, is we're going to do a little bit. Oh, fine. We'll do this. So one of the things you may have noticed from a pattern standpoint is we have a cancellation token source right here. And I hope I have... Do I not have a post-op method for this? Looks like I don't. Well, that's something I'm going to need to add to the written lesson. What we're doing here first is creating, this is a good practice to get into. We're creating what's called a linked cancellation token. I'm going to create a token for this request. I'm going to give us 5 seconds to download the web page. I'm linking it to this shared shutdown cancellation source here. And one of the things I should have done, which I didn't, is we should call post stop right here. In fact, I'll probably add this to the written lesson after this. This is going to basically shut down any in-flight requests. So what this is going to help us do is that in the event that we have some basically HTTP requests that are still being processed in the background at the time this actor needs to terminate, this helps us guarantee that we cleanly shut those down by just invoking this shutdown cancellation token. If you have an actor that manages long-running operations, downloading a web page is generally not that long-running. But for argument's sake, if you do, this little pattern of sticking a cancellation token source in your private fields and then invoking it when you shut down, A+. That's usually a pretty good way to make sure we don't leak stuff after the actor is supposed to be done terminating. Now, the next thing we're going to go and do, if I pull up our document here, is we're going to go ahead and let's grab all this good stuff right here and explain what it does. We're going to create a client from our HTTP client factory, and we're going to use a using block on here to make sure that this gets disposed and returned to the pool once we're done with it. This is basic HTTP client management stuff. No rocket science here. We're going to take the absolute URI we're passing in, and we're going to go ahead and download it. That's what this get async does here. We're going to get an HTTP response message back. We're going to take the content from that response message, and we're going to read it as a string. And we're going to keep passing in these cancellation tokens and all these methods. And then finally, we're going to get into some XPath parsing down here, where we're going to take the HTML document, and we're going to load the HTML into it. This is going to begin the process of basically initializing the XPath parser. Now, I believe XPath works kind of using a little bit of lazy evaluation, so it's not going to do anything yet, but it should create a searchable DOM sort of structure for us to start iterating through when we're ready. And then that's what the extract text function we pasted in earlier is going to do. This is going to, if I go to it, have us basically traverse the descendant nodes. We're looking for nodes that are text types. This includes things like paragraphs, spans, lists, bold, italicized, links. And basically, we're just going to grab all the text elements out as long as it doesn't belong to a style node or a script node. Those are the two text nodes we want to ignore. We're going to go ahead and grab the inner text from that. And then we're going to tokenize it by splitting it into all of the individual. So we're going to split it by space, new line. These are both new line characters, and by tab. So we're going to go ahead and kind of split all those out. Let's close that real quick. Go back to our ParserActor. And then after we've extracted all that text, we're basically going to have an enumerable of strings. So we're going to have a bunch of little groups of strings together. We're going to go ahead and basically pass all those strings into our token extraction system here. And then we're going to call chunk, which is a relatively new link method. We're going to say, grab these words into groups of 20 and then return that to the caller. Okay, so that's what we have so far. We haven't actually done any actor stuff yet, so let's go ahead and add that. Let's go ahead and do switch message. We're going to do case. Let me go ahead and do this real quick. Let's go ahead and do using static document commands. Go ahead and add that up there. And then we'll go ahead and do, I think it is a scan document. Go ahead and do this. Add a little break in here. And then what we're going to do is we're going to go ahead and do run task async. And then we'll go ahead and await on handled. Yeah, where it's found. That is not quite right. That was close, but not quite there. Good job, Copilot. We're going to go ahead and do document chunks equals await scan document, and it's going to be document ID. That's what we're going to pass in there. Document chunks, and we're going to go ahead and pass in our document ID again right here. That looks good. And And then I think finally we say we've reached the end of the document. Let's see if this matches what I originally had up here. Yes, it sure does. Minus, we need to try catch block. So let me go ahead and do that real quick. Try. Easy. We'll go ahead and paste that in. Catch. All right, so we get an exception for any reason. We'll go ahead and tell the sender document events dot document scan failed. Pass in the doc, and we'll go ahead and do on x dot message. All right, that looks pretty good. So what is going on here? Run task is a way you can invoke a task asynchronously inside an actor and await on it, while basically not doing stuff that's going to go ahead and basically make access to the actor's state not thread safe. This is going to basically have the actor process all of the awaits as sort of internal message handlers. For lack of a better word, this is going to encapsulate this task inside the actor's context and make the actor basically progress through all these awaits before it's allowed to process its next message. So this helps preserve actor messaging order while still letting us use awaits inside of it. That's what the run task does. When we call receive async on a receive actor, it's actually doing this internally. So that's what's going on here with all this code. And then I don't think I need to define any other handlers necessarily. This little bit of code right here is useful to know. So awaiting inside an actor is useful if you want to be able to block the flow of execution. The actor is not going to begin processing any other messages until its async state machine completely finishes, which is basically how every other piece of code in .NET works. But with actors, we also have the ability to use PipeTo if we want to. PipeTo is an extension method we can apply on the end of a task. Like here's an example from another project that I mentioned. And by the way, the links to all these lessons will be inside the description of these videos. So make sure you're taking a look at those. But if we want to go ahead and download a web page and have it asynchronously deliver the results back to us, we can use the PipeTo method to go and do that, where it'll take the task returned by this function and deliver its output back to us as a message. This means that the actor can spawn a whole bunch of tasks that run outside of the actor, so it runs outside the actor's context, but the results will all be delivered back to us as messages so we can begin processing them again inside the actor's context. And we have a nice video here that kind of contrasts async await versus PipeTo, which will also give you some kind of good details into the performance impact of all these traits as well. So I think with this, we're done implementing async await. Let's go ahead and move on to the next lesson, which is all about using Akka.Hosting and working with routers and dependency injection. These are all the elements we need to actually get our ParserActor to work correctly. So let's take a look at that next. So we've mentioned Akka hosting in passing several times throughout Unit 1 of Bootcamp so far. Now we're actually going to learn how it really works for real under the covers here. Akka hosting's sort of reason for existence is it's really meant to be a pit of success pattern for working with all of the modern practices that were introduced as part of .NET Core, namely the Microsoft.Extensions ecosystem. So Akka.Hosting is sort of Akka.NET's integration point for working with Microsoft.Extensions.Hosting, logging, dependency injection, configuration, health checks, and more. So that's kind of the basis for it. And this template that we're using here already has it installed. All we need to do now is just adjust the method calls we have so far to work with our actors that we've been creating. So what we're going to do so far is we're going to go ahead and clean up the solution. First thing we're going to do is go to program.cs, and I'm going to delete all of these actor registrations here, and then I'm going to delete the hello actor, I'm going to delete that, and I'm going to delete the timer actor from our solution. We are not going to need either of those anymore, so I'll go ahead and recompile them, and that should all be working fine. Great. Okay, looking good so far. So the next thing that we want to go ahead and do in order to begin actually incorporating our actors we've been building as part of Akka Word Counter 2 into our application, the first thing we need to do is register any dependent services we might have. And the big one, as you can see here, is the HTTP client factory. That's a dependency the ParserActor is going to need. So what I'm going to do here is before I call add Akka, I'm going to go ahead and call services.add HTTP clients. I'm going to need to import a namespace, and we should be good to go there. So that's all working. That should be the only external dependency we need. Now, if we had a more enterprisey application where we had things like databases or authorization services or external web APIs needed to call, you might need a fair bit more configuration than that. In fact, I think we are going to include towards the very end of this unit, we're going to go ahead and include a little bit of configuration stuff for getting a strongly typed, using basically a strongly typed set of options classes from Microsoft.Extensions.Configuration. We are going to do some of that towards the end here. But for the time being, this is all we need to really get going so far. Now, if we keep going here, the next thing we're going to do is learn how to configure logging. I personally really like working with Microsoft.Extensions.Logging. Now, Akka.net's logging system predates Microsoft.Extensions by quite a bit. We really like using our built-in iLogging adapter, and the reason being is that one of the ways that the logging adapter is designed is A, it's designed to be very low allocation. B, it automatically defers all string allocations that you need for rendering a log. That all happens out of band with your actors, so long as you use this sort of, string formatting basic syntax like this. The other reason why we like the logging adapter is it offloads the entire logging pipeline to a set of dedicated actors. We've seen all sorts of weird stuff over the years with Serialog, Microsoft.Extensions.Loggers, where people are able to do things like use logging to files or logging to whatever to essentially create a global synchronization mechanism through their logs by accident. Where if that file gets locked up, it basically blocks all of the iLoggers from Microsoft.Extensions or the Serialog loggers or whatever. And that can cause these massive surges in bag pressure that happen globally all at once. It's just happens as a result of not basically having control over how the downstream logging system works. The iLogging adapter in Akka.net prevents any of that from happening. All that will end up occurring is memory pressure will build up inside some actor that's managed by the system hierarchy, and that's it. We do not want to stop your actors from doing their job just because there's an issue in the logging pipeline. Having telemetry have a negative side effect on actual application functionality is an intensely stupid design choice. We do not do that. That is one of the reasons why we continue to prefer to use our iLogging adapter, even though Microsoft.Extensions has been around for some time. Now, that being said, I love using the integration with Microsoft.Extensions because it lets me have my cake and eat it too. Gives me my ability to make sure that we have a non-blocking logging pipeline. And it also allows me to do things like integrate OpenTelemetry with Akka.net's built-in logging system. So I'm going to go ahead and copy this little bit of code. I'm going to go to program.cs, and I'm going to go ahead and do builder.configure loggers, and let me get rid of the extra period there. And this will make sure that we tie in to the Microsoft.Extensions.logging ecosystem. That's all we really need. There's other stuff we can do here to adjust our logging if we want. I could go ahead and say, log config on start equals true. This will go ahead and perform a dump of all the HOCON configuration options Akka.net has basically internally. So that's pretty useful if you need to debug your, let's say, logging, your configuration inside some environment. But for the time being, we're just going to roll with this. Now, the next thing we need to learn how to do is we want to actually configure Akka Hosting to launch our custom actors. You just saw me delete all the configuration that was built directly into the Akka.Templates output. Well, we want to go ahead and start launching our own actors now. So one thing I'm going to do is create a new folder called config. Let me do that real quick. We'll create a new folder here, config. And then we're going to create a new static class called actorconfigurations.cs. Let's do this. Actor configurations. We'll make this a static class. Now, I know what we're going to do here. This is a pattern that is super useful for being able to get your actor's configuration under test coverage. We are going to copy this little bit of code right here, and we're going to pass this in. This is our function we're going to use for spawning the word counter manager. This is the actor that creates all those individual document word counter actors using the child per entity pattern. So we're going to spawn the word counter manager using this with actors statement right here. This is going to register this function, which will run as soon as the application starts up. So the way Akka hosting works behind the scenes is when we call add Akka, this is going to register an I-hosted service that's going to create the actor system for us and manage it in the background. In the event that our process needs to exit, this will cause the actor system and it will terminate, and we will wait gracefully for that termination to complete. That's super useful, particularly when you start building things like Akka.clustered applications. But that's one thing that this will do for us. The other thing that it'll do is it'll execute all of these delegates for being able to start these actors. It'll execute these delegates in the original order in which they were registered. So this first little delegate we're going to register here, we're going to create the word counter manager actor here using props. We're going to pass that into the actor of method. That's what the actor system is right here. And then we're going to go ahead and register the word counter manager into the actor registry. So far, so good. Now, as we keep going down here, the next thing we need to do is we need to add the parser actors. Now, as we know, the parser actors depend on the HTTP client factory that we passed in before. So we're going to need to use this third parameter right here, the dependency resolver. This is the integration point between Akka.net and the Microsoft.Extensions.Dependency injection ecosystem. So let me copy this function. I'm going to pass that in down here. Now, all of these methods that we're creating so far, these are all extensions off of the Akka configuration builder. That is basically the equivalent of like the iService collection, but for Akka.net. So we want to go ahead and use the Akka configuration builder as our sort of building block here. And all of our configuration is going to be defined as extension methods of this little builder pattern that we're creating. So down here, we're going to call with actors again. We're going to take the actor system, the registry, and the resolver. And then we're going to call this resolver.props ParserActor. Resolver.props is going to use Microsoft.Extensions.di to basically inject into this actor any constructor arguments it might have. But this function will also allow us to blend DI'd arguments with non-DI'd arguments. So for instance, if I go back to our DocumentWordCounterActor, if I needed to pass in, let's say, this absolute URI needed to be different for every single instance of this actor, but it also took an HTTP client factory like this, and I wanted to DI this, but not DI that. Well, if I go back to my little configuration here, I could pass in my new absolute URI, I don't know, URI.try, create, I don't know. Whatever. I can go and pass that in. This would basically automatically match this parameter with the basically manually supplied argument. And it can automatically compute which blend of arguments need to be passed in manually via that input versus which ones can be resolved from the container. It'll do all of that good stuff for you so you don't have to think about it or worry about it yourself. That's very useful and allows us to basically use DI in conjunction with maybe like child per entity pattern and that type of thing. So that's all looking pretty good. Now, the next thing you'll notice down here is I created a round robin pool of parser actors. This means that rather than just a single instance of ParserActor, we're actually going to be running with 5 of them that are load balanced using a round robin distribution strategy. This is one of the router types that's built into Akka.net. And in fact, if we scroll a little bit further down here, we have a couple of different router types. We have pool routers, which basically creates an identical pool of routees from the same props. These are all designed to be local actors primarily. Then we have group routers, which are designed to distribute messages to externally created routees using their actor path. And like I mentioned here, this is primarily for use in networked scenarios like Akka.cluster, for instance. So when we go ahead and we take these props created from this resolver.props method here and apply a router to it, it means we're going to get 5 of this actor plus a router on top of it, not just one instance of this parser actor. That way we can achieve a higher degree of parallelism. We can process that many more pages in parallel doing it this way versus what we could achieve before. I should also mention there's a pretty significant performance difference between routers and normal actors. A normal Akka.net actor can do something like 7 to 8 million messages a second. That's with a very lightweight receive handler defined. A router can do like tenfold that, like 50 to 60 million messages a second. And that's because routers do not have a typical mailbox. They can process messages concurrently. So that's what's going on there. Now, the next thing I want to kind of focus on real quick here is dependency life cycles. Back in the old days of Akka.net, we tried to manage this for you, and it was a dismal failure for one really simple reason, which is that actors can live forever. You can have actors whose lifespans are measured in months or years. This is very, very different from something like ASP.NET Core, where an ASP.NET Core application's reason for existence is managing HTTP requests. those requests almost always have lifespans that are measured in, milliseconds, if not, maybe seconds if you have a really slow application. Therefore, those dependencies don't exist for very long. Therefore, it's very common to inject transient dependencies into, the constructor of a HTTP controller or whatever. Trying to apply that same methodology to actors, which have much longer lifespans, does not result in happiness. It is a bit of a problem. So if you want to try to work with more short-lived objects, what you need to do instead of injecting those short-lived objects into the actor's constructor is you need to inject in the iService provider directly, and then have that service provider create a scope. That scope can be used to go ahead and resolve dependencies, and then when that scope gets disposed, those dependencies automatically get cleaned up. This is basically what ASP.NET does automatically for you. You just have to do it manually inside Akka.NET because the life cycles can be so variable. So that's one little word of caution you should know about DI with Akka.NET. Because actors are so flexible and because they can live forever, you're going to have to manually kind of make some decisions about how you manage dependency injection scopes. Don't expect the framework to do that for you. We will probably never do that ever again. So there you go. Now, that should do it so far for integrating all of our actors that we've developed up to this point directly into program.cs. The next thing we're going to need to learn how to do is we want to take some of these configurations we've just produced and we want to get them under test coverage. So we're going to go ahead and do that by learning how to leverage the Akka.Hosting.TestKit next. All right, so for the next lesson here, we're going to learn how to integration test all of the Akka hosting config code we just created using the Akka.Hosting.TestKit. Now, we've already installed this. We kind of did that earlier. But the basic gist behind the Akka.Hosting.TestKit is to take some of the same tools that worked so well for the, basically creating a new actor system each time and everything else, all the stuff we did in the regular test kit. We're going to do that and then supercharge it this time, which is we're going to create a brand new host for each test method. We're going to create a real service collection and a real service provider. No fakes or mocks. We're going to use the real dependency injection system for real to go ahead and do everything under our roof. And then we're going to bring all of the same testing functionality from the Akka.TestKit into an environment where we can use the Akka configuration builder. So the idea behind this is to basically integration test everything that we've already produced using the Akka configuration builder and everything else. So we're going to author our very first integration test. So what I'm going to go ahead and do is, I guess we're testing the ParserActor this time around. So let's go ahead and create a brand new test down here. We'll call this ParserActor specs. Do that. We're going to go ahead and inherit from the test kit, and I'm going to go ahead and implement these missing members here. And we're going to go ahead and use this extension method we just defined, the add ParserActors. Now, we're not quite done yet. The other thing we also need to do is we need to override the configure services method. Specifically, we need to go ahead and add the HTTP client. Now, we don't need to add Akka. That's already going to happen automatically as a result of the way the Akka.Hosting.TestKit is built. The other thing we're going to do here for good measure is we're going to create the ParserActor specs, and we're going to have this take an ITestOutput helper in its constructor. Yeah, that should be fine. Okay, all of that looks good so far. That should be everything we need to start working on the specification. Now, let's see. I guess one other thing they did is we got to go and define a ParserActor URI. We're going to use the Akka.NET homepage for this. That seems fine. And then, let's see. I guess they also set the log level to debug. Oh, sure. Okay, why not? We can do that too. That doesn't really hurt anything. Let me go down here, configure that. That all looks good. And now let's go ahead and work on our test. We'll call this public async task. ParserActor should work correctly. We're not doing much other than just kind of testing the happy path here. And the way this is designed, we're using that arrange act assert pattern. In fact, I'm going to go ahead and copy this and paste it in here. All right. Now, what are we doing here? The first thing you'll notice is that we're going to call actor registry.getAsync. We're going to resolve the ParserActor that was created here via this method, and we're going to use that as part of the test. That's kind of the first step here. So we're going to resolve the actor. Next, we're going to create a test probe. For all intents and purposes, a test probe is basically just like creating a new instance of the test actor. So we're going to create a test probe, and we're going to send that as we're going to mark that as the sender to the ParserActor here. We're going to go ahead and pass along the scan document command. We're going to pass in our unique URI. All that stuff should work. And then we're going to expect at least one words found message. We should get at least one of these. And then afterwards, we're going to look for a end of document reached message to arrive as well. We don't know how many words are going to get found on that home page. This is a live website, so unless, the URL, I don't know, disappeared or something, this test should work in perpetuity. But we have no idea how many words will be found on the page. So let's go ahead and run this real quick. See what happens here. Okie dokie. All right, and everything passed. Let me run this one more time and get test coverage data. Let's do that real quickly. All right, so all of that got covered. Let's take a look at our testing configuration. And lo and behold, what we can see here is that our entire configuration is now under test coverage. That's what the green means. This sort of like gray means this is not currently covered by any tests, which makes sense. We're not even calling this method anywhere yet. But now we know that our configuration for working with these parser actors in production has also been thoroughly tested. We have confidence that it will do what we expect moving forward. We also know that the DI stuff that we set up will also work correctly. Otherwise, the parser actor wouldn't have produced any data whatsoever. So this gives us the confidence we need to move on to the next part of our lesson here, which is, let me go ahead and dive down here, which is we're going to go ahead and move on to learning how to leverage IOptions and Microsoft.Extensions.Configuration with our actors as well. Okay, so in this unit, we're going to probably spend a little bit of time. This is a really good productionization concern, which is how to leverage the options pattern from Microsoft.Extensions.Configuration with Akka.net. So what we're first going to do is we're going to go ahead and define a strongly typed configuration, which is just this little class right here, word counter settings with a set of document URIs. This is how we're going to tell Akka Word Counter 2 which documents to download. That's what we're going to do here. Let's go ahead and add this class here, word counter settings. Go ahead and paste that in. And that all looks fine. Nothing revolutionary there. All right, that's all well and good. Well, the next thing we need to do is we also need to add an app settings.json file in order for us to have some configuration to parse in the first place. So let's go ahead and copy this JSON. We're going to go to our project. We're going to go ahead and add configuration files, app settings.json. Looks good. Paste that in there. That all looks good. And then one important thing we need to do is we have to go ahead and tell MS Build, hey, make sure you remember to copy our app settings.json file. So let me go to properties, and we want to change the build action to content, and then say copy if newer, or copy always. Either one's fine. Go ahead and do that. That'll go ahead and make sure our JSON file always gets copied into our build output folder. Or if we do something like build a Docker image using the .NET Docker SDK, this will make sure that file ends up where it needs to go. So that's good. All right, so the app settings.json file is there. Now, the next thing we need to take a look at is leveraging the options pattern. Now, the options pattern in Microsoft.Extensions.Configuration lets you do all sorts of stuff, like have reloadable configuration and stuff like that. Dude, I don't think any of that's a good idea. We're just going to roll with like being able to easily parse and bind into configuration and then pass around our config to our actors when we start up. That's a much simpler, more achievable, and by the way, much easier to reason about goal than all that stuff. So the first thing we're going to do here is we're going to go ahead and add inside our word counter settings file, we're going to go ahead and add an IValidateOptions type right here. This is going to give us the ability to validate the content in our app settings.json before we bind it to our word counter settings object. So this will kind of give us the ability to validate our configuration at startup. This is universally a really, really good idea. Let's go ahead and copy that. I'm going to go over to my word counter settings file. Let's paste that. And let me go ahead and import these namespaces. All right, so what's going on here? Well, this validate function, this is going to take the configuration section name and the configuration that we've bound so far. And what we're going to do is produce a list of errors. So for instance, if any of these document URIs, if we don't have any, we're going to go ahead and say there needs to be at least one URL. We're also going to check to see if these document URIs are absolute. We're going to go ahead and check that before we try basically turning any of these into our absolute URI data structure, because that'll throw an exception. And so if either of these constraints fails, we're going to go ahead and add an error message down here. Now you could get a little bit more detail than this if you want. In fact, let's do a little example here. Let me go ahead and just comment that out. We'll go ahead and do for each, we'll say check all URIs to see if they are absolute. There we go. Now this will tell us which URI was not absolute. That's an improvement. We should stick with that. So I might even contribute this back to the original code. So this looks good. If errors.count equals 0, then we go ahead and return that the configuration is valid. If there's at least one error, we return the set of them back. This will show up in a nice big angry startup log. Now down here, we have a little extension method class designed to get our validator and our options all kind of plugged into our iService collection. So what we're going to do here is register our validator as a singleton, since you only ever need one instance of it. And then we're going to use this method down here, add options with validate on start. We're going to basically pass in our options type, word count settings. And then we're going to say, here's the configuration section you should pull this value from, word counter, which corresponds to this. This is good. This is going to cause our application to crash if it has an illegal configuration. There is never a set of circumstances where you want anything different to happen, in my opinion. So we're going to go here to our host builder, and we're going to do services, add word counter settings, and import that. And that should give us the ability to go ahead and make sure that we have some viable word counter settings here. Now notice we're still not running our actor system at all, but if I go and run our application, we are going to go ahead and get an exception. Document URIs must contain at least one URI. So we still have a little bit of a problem here somewhere. And it looks like that failed once again. So I'm going to need to go ahead and double check. Maybe there's something in here I should be taking a look at that we didn't do the right way. And of course there is. What we need to do here is add this little bit of code to the start of our host builder, which is telling it which configuration sources we should be looking for. And what we're going to add here is a default app settings.json, and we're going to mark that file as optional. We're then also going to add an environment-specific app settings.json if we want to. And then finally, we add environment variables. This is kind of my preferred order for setting up configuration like this. This just helps ensure that if I need to overwrite something with an environment variable, which is really common for me to do in environments like Docker and Kubernetes, that means that the environment variable gets the final say. So let me go ahead and add this to our program.cs. Let's go here. We'll go ahead and do host builder dot, and let me get rid of that. Add JSON file. All right, so we've included all of that in there. That looks good. Let me go ahead and compile this. Now let's try running this again and see if it succeeds. All right. We're not getting any startup errors this time. We're also not getting any logs either. That's because the actor system is not going to say anything. We're not doing any logging right now because there's no actors. So, okay, looks like we fixed that problem. So I'll shut that down. Now, our host builder does look like this. And now we have our configuration in place and we're ready to go. The final step we need in order to finish Unit-1 of Bootcamp is we need to put it all together. We need to go ahead and implement the WordCountJobActor, the actor that's going to basically organize the other three actors we've created and get them all to play nicely together in one orchestrated movement inside our application. So let's go ahead and transition to doing that and see if we can wrap up Unit 1 of Akka.NET Bootcamp. So now we're on to the final lesson of Akka.NET Bootcamp Unit 1, which is we're going to go ahead and write a little saga to compose all the components that we've built so far together and finally finish the application. What's the saga pattern? It's, yeah, this is funny. Basically, it's a term invented by message queue and cloud vendors to turn finite state machines into purchasable products. That is by and large true. Basically, a saga really is just a type of finite state machine, but really it's kind of a finite state machine that's focused on coordination / orchestration between different asynchronous or in many cases distributed components. We're just going to focus on working with some local asynchronous actors there. This is all in process. So it's not really a saga in the same sense that it might be in a traditional distributed systems environment. That's not really an important distinction. So for the time being, we got to think a little bit about how we're going to model the stateful behavior of our saga. There's two different schools of thought on how to model a workflow, and which one you choose depends very much on your business context. There's a finite stream, entities that have discrete beginnings and ends, infinite streams, entities that don't. So this is definitely a finite stream. We basically get a set of documents that need to be counted. The stream is over. Once we get all the counts back, the end. It's a finite stream. That's very easy to model. An infinite stream is a little bit more interesting. And this is usually a better tool for something like Akka.Cluster sharding, which we have a video on, which means that You might have a long-lived entity that gets a small burst of events and then gets shut down, isn't used for a couple months, and then gets another burst of events later in the future. That's really totally possible for a lot of different domains, like analytics, for instance, would be a good example of that. We have some user that basically logs in, does some stuff, and then you don't see them again for several months. That might be totally an example of an infinite stream that's highly intermittent. For this application, we're focusing on our WordCountJobActor, which is a very simple finite stream. We get our set of documents that need to be scanned initially. So that's the scan documents command. We then use that to go ahead and kick off some work to the ParserActor. ParserActor is going to produce some events back, which we need to route to the word counter manager. And then finally, once all of the word counter actors are done doing their tabulation, we should get a counts for tabulated documents for each document that was listed in the scan documents message. Once the last one of those is returned to us, we're done, and we can go ahead and log all of our results out to the console. Okay, so here's what our workflow is going to end up looking like. So we basically have our onReceive method here. We're going to wait until we get that scan documents command. Any other messages that we can't process right now are going to end up in the stash, which is an Akka Streams tool we're going to learn about in just a second. But once we get that scan documents command, we're ready to run. We're going to shift into the running behavior, and what we're going to do is we're going to go ahead and stream scan document commands to all of the parser actors. And as those parser actors are working, they're going to go ahead and begin streaming some of those basic responses to the word counter actors. That's what's going to be happening here. We're also going to send fetch counts messages to all of the word counter actors too. And we're going to wait for all those counts to be returned to us. Once we get all of the counts tabulated for every document, our job will be finished and we will shut ourselves down. That's how we're going to end the finite stream. There's nothing for us left to do once the job's complete. So on that note, we're going to go ahead and implement a little prerequisite here. I'm going to add a little class called collection utilities. This is just going to help us merge all of our different documents together, each one containing the word counts for a single actor. We're going to go ahead and just copy and paste this into a new file called collection utilities. So we're going to do that real quickly. Let's go here, add a new class, call this collection utilities, and I'll paste that in. That all looks good. This is just using a little bit of link basically to go and tabulate everything together. Nothing too special. So that should be that. And now we're going to move on to the word count job actor. This is our little saga. Now this actor is using two pieces of infrastructure that we haven't seen before. IWithStash, which gives us a place to store messages we can't process right now, and IWithTimers, which gives us the ability to schedule arbitrary periodic messages that will either recur or delayed messages that we will receive in the future. The ReceiveTimeout is like a subset of what IWithTimers does. IWithTimers is more generalizable. So that's what we're going to do here. So I am going to go ahead and copy this and paste it into my code. Again, if you're following this online, you should have this document up and you should be typing this yourself so you build some muscle memory. I'm a very experienced Akka.NET user. I don't need to. So I'm going to go ahead and copy this. And we're going to paste this into, let's see, what was the name of this actor again? WordCountJobActor. Let me copy that first. WordCountJobActor. Let's go here, actors, add, paste that in. Let me go and copy this file. Okay, now let's talk through what this actor is doing. So untyped actor with a stash with timers. This actor takes two different dependencies through its constructor. An IRequiredActor of WordCounterManager and an IRequiredActor of ParserActor. This is how we take the actor registry and make it injectable into an actor's constructor, or really any constructor. It could be an MVC controller, could be any number of things. But this is how we typically do that. Next, we have our stash and our timers. These two properties are going to get populated by Akka.NET using this public setter after your actor begins. So we can set this, we can basically null the nullability warning here. We know this will get populated automatically by Akka.NET. And then finally, we have our internal state, our hash set of subscribers, actors who want to know about the status of the entire completed job. And then we have all of our documents we need to process, and we also have the word counts for each individual document. So this is kind of keeping track of our processing status, which is this little enum right here. This is keeping track of the results once we have them. And then we have a couple of built-in message classes. This job timeout right here, this is just a little singleton. This is our way of knowing that basically we failed to do our processing somehow. So here's what's going to happen next. We are going to inject these IRequired actors into our constructor, and we'll go ahead and see how that gets arranged when we wire this up into Akka hosting in just a second. And then we have our receive method right here. Once we get the scan documents message right here, we're ready to go. We're going to go ahead and log that. And then for each of the different documents we need to scan, we're going to go ahead and store the process for that document. We're then going to tell the ParserActor to begin processing. And then we're going to tell the WordCounterActor to fetch counts for these documents. Basically, we're going to go ahead and set a subscription that once we've completed totaling these documents, send the results back to us. We're then going to shift our behavior to the running state, and we're going to start this timer, job timeout. This message will be sent to us if we don't complete our work within 30 seconds. And the other thing that's kind of nice about this timers construct is that if we shut this actor down, all of its timers will automatically be canceled. So there's no possibility of being able to leak a timer, in other words. And then here's the message stash. We're going to call stash to unstash all in the event that we get the scan documents message. What that's going to have us do is basically dump all the messages that built up in our stash back into the front of our mailbox. Move messages to the front of our mailbox. By declaring our actor as having a stash, we actually are changing the shape of our mailbox to be a double-ended queue rather than a single-ended queue. And the reason why that's an important detail is that stashed messages are always older than anything that's already sitting inside the mailbox. So we want to give those messages that were in the stash a chance to be processed first. That's why we're going to prepend them to the front of the actor's mailbox rather than send them to the back. That's why stash to unstash all is going to get called here. Now, in our default message handling behavior, any other messages you might send to this actor, we're going to buffer for the time being. We're just not going to process those. So we're going to go ahead and buffer them until we receive this job right here. Once we're in our running state, if we get a word found or end of document reached message, we're going to forward those to our word counter manager. This IRequiredActor has a property, ActorRef, which contains the underlying actor reference that was registered with this key. So that's what we're going to do here. Once we get a completed count tabulated for a document, we're going to go ahead and store those word frequencies. We're going to go ahead and record that this processing status was complete. And then we're going to call this function down here, handle completed job maybe. We'll see what that implementation looks like in just a second. If we get a document scan failed, we're going to log an error here. And then we're going to go ahead and basically set that this document's processing status failed with error. We'll call handle job completed maybe here as well. And then when we get a job timeout, we'll go ahead and log an error. We'll go ahead and set all the documents as failed to timeout. And then we're going to force that handle completed job to run. If we get someone who wants to subscribe to all the counts from all documents, we'll add them to our set of senders right here. And then for any other message type we get, we'll go ahead and filter this into the unhandled bucket. Now this handle job completed maybe function, the way this works is that if the job hasn't been completed and if the force property is false, we'll go ahead and just exit. We basically the job's not done yet, and we're not being forced to complete. What this function basically checks to see is that if all documents are in a status of processing, we will go ahead and, all documents are in a status greater than processing. There we go. That means that we're done. So if some documents failed or if some succeeded, we don't really care. All those statuses are higher on our enum than the processing status. That means that we're finished. We can move on. Otherwise, we're going to go ahead and log the statuses of each page. We're then going to merge all the counts together and turn it into this little final output here, which we will then deliver to all subscribers, and then we will shut ourselves down. So there's going to be a lot of little bits of processing that all kind of happen behind the scenes. All these individual document actors that are created by the word counter manager are all going to be doing their totaling. All the parsers are going to be doing their downloading and parsing. This actor isn't in the middle of any of that, really. It's basically just kind of directing traffic. And then once we know we're finished, we're going to go ahead and shut ourselves down. That's all that we really need to go ahead and make this stuff really work behind the scenes. Now, the only reason why we're directly handling these messages rather than having the ParserActor send them directly to the word counter manager is basically so we could also get the document scan failed message back. It was kind of easier and simpler to design the ParserActor to work that way, where it always responds to the original sender, rather than having to have one channel for report scanning failures and then another channel for reporting words found. This is just kind of a simplification thing I decided to do. In a real production system, I might choose to diverge these messaging paths a little bit. So that's that. The word count job actor is now finished. Now, if we scroll down here, we talk about how stashing works. We talked a bit about how IRequiredActor works. The thing we need to do next is we need to add this little bit of config to our actor configurations file. So let's go ahead and do that. Let's go to actor configurations. We're going to add this here. So we're going to go ahead and call this method add_job_actor. We're going to use the resolver.props to create this WordCountJobActor. That way, these IRequiredActor parameters will be injected into this actor's constructor. All right, so that all looks good. And then we're going to add a sort of a composed method here, add application actors. We're going to add the WordCounterActor, the ParserActor, and the JobActor all at the same time. We're going to go ahead and wire these up. If I go down here, we'll go ahead and do builder, add application actors. So now all of our actors should be up and running. But that's not quite the end of the story just yet. We have the actors, but nothing's going to happen if we run the application. The last thing we need to do is add a startup task. One of the things this will let us do inside Akka Hosting is execute an arbitrary piece of code that doesn't create any actors, but it does have access to the actor system and the actor registry, and lets it kind of run after all the actors have been created. So we're going to copy this little piece of code right here, this actor startup, and we're going to tack that on right here. Let's see, add startup, and I guess I need to import these namespaces. That's all working. Okay, so what's happening here? What we're doing is we're going to use the service provider, which we're closing over right here as part of the add Akka method. We're going to use the service provider to get access to the word counter settings. We're going to go ahead and get those options. We're then going to go ahead and use the actor registry to get a reference to the WordCountJobActor. We're then going to take all the documents that were specified in our settings file, and we're just going to get all the absolute URIs right here. We're going to go ahead and do some processing here. And then we're going to tell the job actor to go ahead and scan the documents. And then we're going to ask the job actor, we're going to say, hey, give us all the tabulated document results. We're going to go ahead and use a little ask operation right here. The temporary actor that gets created when we do an ask is going to end up being the subscriber that the WordCountJobActor memorizes. And then after we get that result back, we're going to iterate over the results and just dump them to the console. And I guess I have an extra semicolon right here. Let me delete that. Let's see what happens when we try running this. And boom, we went ahead and we got all of our word counts back. Now, it looks like we probably could do a little bit more to tokenize this cleanly. We're getting some commas and periods and some markdown text in here, all sorts of goofy stuff. So there's probably a bit more we could do to try to sanitize some of the text that's coming out of this application. I'll leave that as an exercise for you, the reader. But otherwise, there we have it. Our application is now working and intact. And for all intents and purposes, we have completed Unit 1 of Akka.NET Bootcamp. So that's it. We're now done with Akka.NET Bootcamp Unit 1. The next thing I would go ahead and do is first I would go ahead and sign up for email notifications about future Akka.NET Bootcamp lessons. We're planning on adding a new unit on ASP.NET Core integration. That's probably the next one we for sure have announced already. We'll probably do some ones on Akka.Cluster, Akka Streams, and Akka.Persistence as well. But for the time being, I'd strongly recommend going ahead and subscribing to this. Otherwise, you should check out the rest of the Akka.NET blog and maybe check out our YouTube channel to go ahead and get some more information about Akka.NET and start your programming journey for real. The other thing you could potentially do that might be worth your time is taking a look at some of the bigger code samples we have, such as in the Petabridge GitHub organization, we have this Akka.NET code samples repo along with DrawTogether.NET and WebCrawler. All of these ones are great samples to go ahead and learn how to build slightly larger Akka.NET solutions with. So thank you very much for your time. We appreciate it, and we hope you enjoyed Akka.NET Bootcamp. Well, that'll do it for this video. If you found this video useful, please don't forget to check the description to find links to other resources we may have included, so blog posts, GitHub code samples, other videos, so on. And as always, don't forget to like and subscribe and ring the bell for notifications. We'll catch you next time. Thank you very much.